The main objective of this experiment is to understand metallurgical sample preparation methods and understand how to do optical metallography, as well as to introduce students to the fundamental procedures of heat treatment. This experiment also has students observe the changes in the sample's microstructure through the use of heat treatment and cooling of steel, as well as document the change in mechanical properties and related to the change in the sample's microstructure. Not all steels will meet their exact physical design specification required straight from the manufacturer. To adjust the physical properties of steel, we can heat treat the steel until it meets the required specification. Different types of heat treating include annealing, tempering, and quenching. Variations in each of these steps will produce many different properties of steel, with the biggest variation being time and temperature. According to the American Society for Metals Handbook, it is recommended that 1018 steel is annealed at temperatures ranging from 855 degrees Celsius to 900 degrees Celsius, and furnace cooled at a rate of 28 Celsius per hour. Theoretically, this will produce a Rockwell hardness ranging somewhere between 111 and 149. In this experiment, we annealed our sample at 1000 degrees Celsius and varied the quench rate in order to investigate the effects. Next, we either quench, furnace cool, or air cool our sample. As we saw in our experiment, these methods correspond to fast cooling rate, moderate cooling rate, and slow cooling rate, respectively. Then, we investigate the effects of tempering on our sample's hardness and its microstructure. Tempering is when we heat our metal sample to around half its anneal temperature, as so to reduce excessive hardness and increase its toughness.
Because ordinary resin mounts are too weak to support steel during polishing, bakelite is needed to form a stronger mount. Bakelite, though stronger, requires mounting in a high-pressure furnace to properly form and mount your sample. Once mounted, the polishing process can begin. Polishing is fairly straightforward in that you polish at low grit and go higher until the surface is sufficiently smooth for etching. Our experiment used 2% nitol for the first etchant and oxalic acid for the second etchant. Other etchants should also work, so just follow the etchant instructions when using.
To analyze the results of the experiment, the samples were either viewed under an optical microscope or with differential imaging contrast, or under a confocal laser scanning microscope. This allows us to determine the different microstructures present and to possibly predict the physical properties of the sample. Also, Vickers microhardness measurements were conducted, and the results were recorded for all samples. Ideally, the microhardness measurements would show that the hardness increases with increasing cooling rate, and the hardness decreases with tempering.
Currently, we got two possible situations besides label the wrong result with wrong group. One is tempered martensite embrittlement. Tempered embrittlement refers to decrease in notch toughness of alloy steels when heated in or cooled slowly through a temperature range of 400 degree to 600 degree. Tempered embrittlement can also occur as a result of isothermal exposure to this temperature range. The occurrence of tempered embrittlement can be determined by measuring the change in ductile to brittle transition temperature with a notched bar impact test, before and after heat treatment. In most cases, the hardness and the tensile properties of material will not show any change as a result of embrittlement, but the transition temperature can rise by as much as 100 degrees for embrittlement heat treatment. Another possibility is tempered brittleness. Tempered brittleness is a loss of ductility caused in certain steels when they are held or slowly cooled through the temperature range from 300 to 600. This effect most commonly seen in nickel, chromium steels and is due to precipitation of carbides in areas between the crystal in their structure. The impurity in steel may cause our 1080 steel become nickel chromium-like steel.
On the figure to the left, we see an excellent example of the martensitic structure formed when the steel is cooled very quickly in water. On the figure to the right, the sample is air-cooled and does not have any martensitic structures. Small domains of perlite can be seen in the circled areas in both of these samples. Perlite contains layered structures of lightly colored ferrite and dark colored cementite. There's only a small amount of perlite in both samples because the carbon content is hypoeutectic, facilitating growth of protectoid ferrite phase before perlite can form. There are many different types of microconstituents that are possible in steel. First one is perlite, which is a laminar structure composed of alternating layers of ferrite and cementite. Martensite is a highly brittle structure with a needle-like appearance. Bainite is a plate structure composed of ferrite and cementite formed by isothermal transformation of austenite. Spheroidites are spheroid structures formed from isothermal transformation over long periods of time, and it's the most ductile form of steel. Ferrite is a ceramic-like form of iron with extremely low carbon content due to low carbon solubility. Cementite, which is iron carbine, whose weight contains around 6.67% of carbon, which makes it very hard and brittle. And austenite, which is the soft form of steel, which readily decomposes into perlite or martensite.
Here are the references we used for our presentation. I hope you enjoyed this video, and thank you for watching.